Introduction: a new reality. Our universe operates on principles that often defy common sense. The world of quantum mechanics, governing the realm of atoms and subatomic particles, is filled with wonder and mystery. It's a bizarre world, where particles can be in two places at once, and information seems to travel faster than light. These aren't just theoretical concepts, they are the bedrock of modern technology, driving innovations from lasers and transistors to medical imaging and nuclear energy. The journey into the quantum realm begins with a paradigm shift. We must abandon our classical intuitions about the world and embrace a new set of rules that often appear counterintuitive and strange. This is not to say that our classical understanding of the world is wrong, it's simply incomplete. Quantum mechanics provides a deeper, more fundamental description of reality, one that encompasses the classical world as a special case. Imagine a world where a single object can be in multiple states at the same time, where information can be instantaneously shared across vast distances, and where particles can pass through impenetrable barriers. This is the world of quantum mechanics, a world that challenges our understanding of reality and opens up new frontiers of scientific exploration. It's a world where the seemingly impossible becomes possible, where the familiar laws of physics break down, and where the universe reveals its most profound secrets. The implications of quantum mechanics extend far beyond the laboratory. They touch upon the very nature of reality, the limits of knowledge, and the future of technology. As we delve deeper into this enigmatic realm, we uncover new possibilities for computation, communication, and medicine. We gain a deeper appreciation for the interconnectedness of the universe and the fundamental mysteries that lie at its heart. The journey into the quantum realm is an invitation to explore the unknown, to challenge our assumptions, and to marvel at the wonders of the universe at its most fundamental level. Duality, a dance of waves and particles. One of the most fundamental concepts in quantum mechanics is wave-particle duality. This principle states that every particle can also behave like a wave, and every wave can exhibit particle-like properties. It's a strange idea, like imagining a baseball suddenly spreading out like ripples in a pond, or ocean waves crashing onto the shore as a barrage of tiny marbles. This duality is not just a theoretical curiosity, it has been experimentally confirmed countless times. For example, in the famous double-slit experiment, electrons are fired at a screen with two slits. Instead of forming two distinct bands on the screen, as one might expect from particles, the electrons create an interference pattern, characteristic of waves. This suggests that each electron passes through both slits simultaneously, interfering with itself like a wave. The concept of wave-particle duality is essential for understanding the behavior of light. Light can act like a wave, diffracting and interfering like water waves, but it can also behave like a particle carrying discrete packets of energy called photons. This duality is the foundation of technologies like lasers, which exploit the wave-like properties of light to create highly focused beams, and solar panels, which capture the energy of individual photons to generate electricity. Wave-particle duality is a profound concept that forces us to rethink our understanding of the fundamental building blocks of the universe. It suggests that the world is not neatly divided into particles and waves, but rather that these two seemingly contradictory aspects of reality are inextricably intertwined. This duality is a testament to the strangeness and wonder of the quantum realm, a realm where the familiar rules of classical physics break down and where the universe reveals its most enigmatic secrets. Superposition, embracing uncertainty. Another cornerstone of quantum mechanics is the concept of superposition. In the quantum world, particles can exist in multiple states simultaneously. It's like a coin spinning in the air, being both heads and tails at the same time until it finally lands and settles into a definite state. This is a stark contrast to our classical experience, where objects exist in a single, well-defined state at any given time. Superposition is not just a theoretical concept. It has been experimentally verified in numerous experiments. For example, in a quantum computer, a single quantum bit, or qubit, can represent both 0 and 1 simultaneously, allowing for a vast increase in computational power. This ability to exist in multiple states simultaneously is what makes quantum computers so powerful, potentially enabling them to solve problems that are intractable for classical computers. Imagine a spinning coin suspended in mid-air, embodying both heads and tails simultaneously. This is the essence of superposition, a concept that challenges our classical intuitions about the nature of reality. In the quantum realm, particles exist in a haze of possibilities, a superposition of states, until an observation forces them to collapse into a definite state. This profound concept has far-reaching implications, not just for our understanding of the universe, but also for the development of new technologies. Quantum computers, leveraging the power of superposition, hold the promise of revolutionizing fields like medicine, materials science, and artificial intelligence. The ability to harness the uncertainty of the quantum world opens up new frontiers of exploration and innovation, paving the way for a future where the seemingly impossible becomes possible. Entanglement, a mysterious connection. Perhaps the most baffling phenomenon in quantum mechanics is entanglement. When two particles become entangled, their fates are intertwined, regardless of the distance separating them. Measuring the state of one particle instantaneously determines the state of the other, even if they are light years apart. It's as if two coins, flipped on opposite sides of the globe, are somehow linked, with one always landing heads when the other lands tails. This spooky action at a distance, as Einstein famously called it, has been experimentally confirmed countless times. Entangled particles seem to share a connection that transcends space and time, defying our classical intuitions about causality and locality. It's a phenomenon that has puzzled physicists for decades, raising fundamental questions about the nature of reality and the limits of our understanding. Imagine two particles, separated by vast distances, yet inextricably linked. Measuring the state of one instantly determines the state of the other, as if an invisible thread connects them, transmitting information faster than the speed of light. This is the essence of entanglement, a phenomenon that challenges our fundamental understanding of space, time, and causality. Entanglement is not just a theoretical curiosity, it has the potential to revolutionize communication and computing. Quantum cryptography, for example, exploits the properties of entangled particles to create unbreakable codes, ensuring secure communication. Quantum teleportation, another mind-boggling application, leverages entanglement to transfer quantum information between distant locations, opening up new possibilities for communication and information processing.